Hello everyone, welcome to my YouTube channel. And in this series, we will learn and discover ways how to enhance our simulation and coding skills, specifically for vapor compression cycle, which has application in heat pump, HVAC, and R. So let's start from where we left. So in the previous video, you have seen that we have made a vapor compression cycle simple code in Grok, and we have finally successful in discovering the four state points of a simple vapor compression cycle. And when we run it, you can see we can also have the pH diagram, and in this one pH diagram we can see all different refrigerants, their cycle diagram, and their DOMs, so that we can quickly see how and which refrigerant is performing better. And with this we are also having the COP values. So let's move on and let's see what other things we can do in it. For example, to make it more realistic, we will ask Grok to uh, further enhance the applicability of this code. So let's ask in this code, add superheating and subcooling values of 5 degrees Celsius. So this is a number one thing which we want to improve. Another thing which we want to improve in this code is that we can add or make other plots. For example, we will ask make a histogram plot for the COP results. So also we can ask to make a histogram plot for the mass flow rate results, so that we can see clearly the results, COP and mass flow rates. So let's see how Grok responds. And we will continue using Grok because in the previous video you saw Grok is a better platform, a platform as compared to ChatGPT, and it provides correct codes. So here within second you can see it has provided us the code, and it has the similar state points, and it is now storing the results of COP, mass flow rate, work, and condenser duty, and generating pH diagram with saturation DOM, and then printing the results, plotting the pH diagram, and also plotting the COP histogram, which is the additional thing which we have added, and plotting the mass flow rate histogram. So let's copy this code, and here it is telling us what are the things which it has improved, like graphical contents. So let's copy and paste it into a new file and just name it grok 2. Just run and see. So here you can see it has provided us the pH diagram as it was previously providing us. And this, it has provided us a histogram and the histogram of COP. But this histogram is not in that way we need it. We need the COP on the y-axis and refrigerant on the x-axis. So it's not correct. And here is the mass flow rate. So the mass flow rate histogram is also not correct. So it means that we have not provided it enough information, because of which it has provided us wrong histograms. So we will just clear it. We need COP and mass flow rates on y-axis and refrigerant name on x-axis. Please rewrite the code. So you can see, like, the more precise information you provide these platforms, the more better code you get. So sometimes it provides you wrong, or it does not understand what you want. So let's see. Now it's saying like it will modify the previous vapor compression cycle code, incorporate the 5 degrees C superheating and subcooling, and adjust the histogram plots to display COP and mass flow rates on the y-axis with refrigerant names on the x-axis. So here you can see it has provided us new code. Just copy it and paste it and run it, and let's see that has it modified it and corrected it. So first is the pH diagram, which was correct. So second, now you can see the COP comparison. So here you can see in just one glance that which refrigerant is giving you better COP values. So here you can see ammonia is giving better COP, and after that you can see R134A, and then R32 and R410A. So another thing which I would like to add, that you can also save these graphs. You just click on the save and it will take you to your library where you can just save it. So when you will close it, now you will get the mass flow rates. So here you can see ammonia, which has the better COP, has the least mass flow rate, and then it is keep on increasing R32 and then R410A and then R134A. So I also told you in the previous video, like these HFCs, they usually have higher mass flow rates as compared to the natural and hydrocarbons refrigerants due to their thermophysical and thermodynamic properties. So the hydrocarbons and natural compounds or components or refrigerants, they have better thermophysical properties as compared to these HFCs. So here you can see the mass flow rate, COP graph, the pH diagram. So what you can do, you can just change the name of the refrigerants, and you can also add, if you want to add more refrigerants, like in ammonia, instead of ammonia we will just change it to butane, and for our 410, let's change it to propane, and then let's run it again and see how it gives us this pH diagram. So here is its pH diagram, and you can also save it as I told you. And when we will close it, we will get the COP values. So here you can see the COP histogram. Butane is performing best. After that is R134A, then propane, and then R32. When we close it, you will get the mass flow rate histogram. And here you can see again R134A is having the highest mass flow rate, and here butane is having the lowest mass flow rate, and then comes propane, and then comes R32. So you can see like how simply we can just make plots and histograms using a grok just using grok and just asking it what we need. One thing which I just forget to tell you, like in this plots, now you can see that we have also added the superheating. So here you can see the point is above the vapor line and vapor line dome up to 5 degrees Celsius. And similarly here you can see we have also added the subcooling to make it more realistic. So usually in these vapor compression cycles we have superheating and subcooling and isentropic efficiency. So here you can see like we have this isentropic efficiency of 80%, and we have the superheating subcooling which you can easily change, and you can see how the results will change. And also you can change the evaporation temperature and condenser temperature, and you can see how this will vary. For example, let's change the evaporation temperature to, let's suppose, let's go on to minus 10 degrees Celsius, and the condenser temperature just to 50 degrees Celsius. So just to change, check how the things will change. We will run it, and here you can see now the pressure levels has decreased for the evaporator and increased for the condenser. And the pH diagram, you can see the pressure drop in the expansion valves has increased. And here you can see the COP values has also changed because the compression ratio is now increased, the compressor work is increased, and the pressure levels of evaporator and condenser has increased. So the COP values has decreased, but still you can see butane is performing best, and after that is R134A. So the sequence is same, and similarly the mass flow rate is also like butane is having the lowest mass flow rate, but the values have been changed. So in this way you can see like how you can just learn using Grok platform and PyCharm and Python and CoolProp database, and you can see which refrigerant is better, and you can just select a best refrigerant and you can just study it. So thank you very much for watching this video, and in the next video we will go much more deeper inside, and we will explore this grok and this simulation environment, and we will see how other things or how more detailed things or simulation we can make with these freewares, and how much more we can learn. So I will share this code in the description, so you can just copy it and you can use it for yourself. Thank you very much for watching this video, and if you like it, please like and subscribe my channel. Thank you very much.